Hi everyone, my name is Kristina Lerman, and I'm really happy and I'm privileged to give a talk today about my research, which is the stretchy paradox and the origins of perception bias in networks. So let's begin. If you're like me, especially in these days of the pandemic, you've been hanging out a lot on social media sites like Twitter and Facebook, and you've noticed that it's really easy to get stuck in the so-called echo chambers or filter bubbles on Twitter, where you're connected to other people who share very similar views, and you're seeing everybody how like the whole world is agreeing with this. This is my new favorite phrase to describe this effect, was coined by Renee DiResta. She talks about bespoke realities. So I want to talk about, in the rest of my talk, I'll show you how bespoke realities don't just arise out of filter bubbles and echo chambers. You can actually, they're a pretty common consequence of social networks and social networks that basically result in biasing our perceptions of popularity and what we consider as a common consensus and also social norms. So my talk first will introduce what I mean by perception bias and the more interesting case, the majority illusion in networks. I'll explain how these arise as a consequence of the friendship paradox in networks and show you how we can actually, which parts of network give rise to these, how we can actually quantitatively estimate the strength of these effects in many social networks. Okay, so perception bias refers to the fact where individuals misestimate, misperceive some trait or some behavior among their peers. So this arises from the fact that people do not often see the view of the network as a whole, but they only see part of the network, subset of the network, specifically, namely their friends. And the friends, important for understanding this effect, is that friends do not represent a random subset of the entire network. They're a very special subset. They're the subset that you decided to, the nodes that you decided to make connections to. And because of these consequences of decisions that many people made and how they connect, as a consequence of that, an active minority can distort perceptions of many individuals, leading to the effects like the majority illusion and perception bias. One way to explain it, show the mean is actually was created from a demo that was created by Kevin Scholl from Washington Post after he read the paper I published called Majority Illusion in Social Networks. So this paper describes the effect, or this demo describes the effect where you have a network that has, some number of nodes, and a small minority of these nodes have some trait. For example, the small minority of these nodes are blue, whereas the rest of the network is yellow. So if you want to estimate what is the color of the network, you do it by polling the social network. For example, you ask people, what are you? What color are you? And so the people will report, most of the nodes will report, I'm yellow. 3 nodes will report, I'm blue. So you can say, okay, that will give you a pretty good estimate of how many nodes are of each color you have within the network. So you'll conclude that most of the nodes are yellow. But then instead you ask people, well, what color are your friends? People will report something that's completely different. So each node will look at its neighbors, its friends within the network, and see that the majority of them are blue. This is actually true within this network. So many nodes here on the right-hand side, nodes are reporting the majority color of their friends, and most of the nodes will report that majority of their friends are blue. So again, if you ask people what they are, they'll say they're yellow. Many of them will say they're yellow. If you ask people what their friends are, many of them will say, oh, my friends are blue. So while this may seem like a cute artifact of some demo, this actually happens, and it happens all the time in many different networks. For example, many studies have shown that college students, adolescents, overestimate the prevalence of some risky behaviors, for binge drinking, for example. And if you go to a college campus and you ask people how much they drink, this is the left hand, the blue bars, people will report as follows. About 1/3. This is from a survey done at UC Berkeley, so this is actually actual data. So about 1/3 of the people will say, I don't drink anything at parties. And about another quarter will say, I consume 1 or 2 drinks, and another quarter will say, well, I have 3 or less than 4 drinks, 3 or 4 drinks. So about over 70% of the people, so majority of the people will say they drink 4 or fewer drinks at parties. But if instead you rephrase the question and you ask people, how much do your friends drink, you'll get a dramatically different response. So about 70 people will say that percent of the people report their friends having more than 3 or 4 drinks at the parties, 3 or 4 or more. And this coexists in the same network. And this happens not only on college campuses, it happens on social media as well. So here, this is reports of a study we published this year in Nature Communications, where we collected data from Twitter. This was back in the summer of 2014. And we collected data from about 5,000 people. These are called our focal users. And more importantly, we collected their social network neighbors, the contacts. So we knew who they were following, and we also collected the tweets of those people they were following, tweets of their friends, so that we could reconstruct the feeds, the social feeds these people were seeing, what they were seeing within their social feeds. So this was in the summer of 2014. What was happening in 2014? Well, pretty much similar things that are happening this summer as well. This is where Michael Brown was shot by police in Ferguson. So these Ferguson, Michael Brown, they were trending topics in August of 2014. This is when we collected the data. So we did a similar study as the Berkeley drinking campus. We can poll our users. Well, we can actually just see what they were tweeting about, what they were posting about, and how many users were posting about a specific topic. So, for example, here the blue bars show how many people within our sample are using the hashtag Ferguson or FF or World Cup or Ice Bucket Challenge, Mike Brown, and so forth. That's the blue bars. And the orange bars are showing what fraction of friends of these focal users are tweeting about the same topic. So you can see for many of these hashtags, what people see, the fraction of the friends, the fraction of users they see within their social feeds who are using the hashtags is often several times larger than the number of people who are tweeting about the hashtag overall. So this is what we call perception bias. Again, people overestimate the popularity of some topics by seeing more of the friends use it within their social stream. So why does this happen? Actually, this perception bias and majority illusion both are rooted in the friendship paradox. The friendship paradox is first formulated by sociologist Scott Feld in 1991, says that your friends are more popular than you on average. So it means that your friends have more friends than you do, and this applies on average. So more interestingly, several variants of the friendship paradox have been observed. So for any trait, for example, drinking, for any trait that is correlated with popularity. So if it happens that alcoholics or people who have to drink a lot also have more friends, then you'll get generalized friendship paradox for that trait. So for the trait, your friends have more X, whatever the trait is, more X than you do on average. So for example, your friends drink more than you do on average, which is what we observed in the alcohol example. And this leads to perception bias, where some traits some traits appear more popular within social circles of many people than they are in reality. So these are the friendship paradoxes. What's more interesting is actually the strong friendship paradox. So we actually showed in the paper, IC2S2'20 paper in 2014, that Feld's friendship paradox actually generalizes to the median. Instead of using the mean to represent average friends value, average friends popularity, we can use the median. But the paradox still holds in many of the networks we are considering. I will show you in the next slide that it actually holds for many, like vast majority of nodes. So not only are your friends more popular than you on average, actually most of your friends are more popular than you are. And it similarly generalizes, that for any trait, in fact, any trait that's correlated with degree, for example, being wealthy, or being, having more citations probably as well, it will hold true that most of your friends are wealthier than you are, or most of your co-authors have a higher H index than you do on average. We haven't checked yet, but I'm sure it applies as well. And this generalized friendship paradox can also produce majority illusion, where some trait can be rare in the network as a whole, but many people will vastly, dramatically overestimate it. Many people will think that most of their friends have that trait, even though it's rare overall. This is what we call the majority illusion, which must be happening all the time in social media everywhere. So how common are these? Well, these paradoxes are very common. Here I'm giving you Twitter results for social networks of Twitter and Dig, which was a social news aggregator. Was popular several years ago, but I'm sure it holds in other social networks as well. Strong friendship paradox holds. The gray bars show the fraction of Twitter users in the data sample we collected, the fraction of Twitter users who observe the friendship paradox. The gray bars are for the Scott Felt's version of the paradox, what we call the weak paradox, and black bars are for the strong version of the paradox. So as you can see from the bars, like 90% of Twitter users observe that most of the people they follow are more popular than they are. That most of the people, it also holds for all, in directed networks, it holds for all directions. And most of the people who follow you are also more popular than you are. And so forth. Not only that, but actually most of the people you follow are more active on Twitter. They tweet more often than you do. Not on average, but most. It also holds true that information you receive also has that similar paradoxes. Most of your friends, not on average, but most of your friends receive more diverse content and also more viral content. Most of your friends see URLs in their newsfeed that end up spreading farther than the URLs and the content, which we denote by URLs, the content that you receive in your own social feed. So not this last paradox is not quite as ubiquitous as the earlier paradoxes, like the strong friendship and the diversity activity paradox, but it does hold true for most of the users as well. All right, so how do these effects arise? Where do they come from? So we actually have nailed down, we have isolated the role of properties, which network properties are needed to quantitatively explain the strong friendship paradox and the majority illusion. And these network properties actually just need 3 network properties to completely describe the strong friendship paradox effect. The first of them is the very familiar degree distribution. So everybody should know already about the degree distribution. It gives the probability that the node you select at random from a network will have some degree k. So for example, here in the black dots, I'm sure many of you will recognize the familiar Karate Club network. And the plot on the right, chart on the right, shows the degree distribution from that network. The probability that a node has degree 2 or 5 or 6, or the highest degree here is 16 and 17. And in fact, this skew in the degree distribution, the fact that you have some high degree nodes within the network, is what is necessary and required to create the Felt's version of the friendship paradox. In fact, any skewed degree distribution will lead to the paradox. Why? Because these high degree nodes with degrees 16, 17, not only are they very popular, they have many friends, but they also occur in the friendship circles among the friends of many other nodes. So they end up skewing the friend averages, the average popularity of friends for many different nodes. That's why Feld's version of the friendship paradox exists. Also, the next property you need to describe the friendship paradox is the degree assortativity. So as I said earlier at the beginning of this talk, nodes do not link at random, but they select who they want to link to. And this creates, induces correlation among degrees of connected pairs of nodes. This is the so-called joint degree distribution, or as Mark Newman, when he introduced this, he introduced the degree assortativity as a measure of the correlations of the degrees of linked nodes. So social networks can have positive degree assortativity or negative degree assortativity. So, and whether it's positive or negative dramatically changes the structure of the network. So on the right, I'm showing an example of the positive assortativity, where high degree nodes tend to connect to other high degree nodes, and low degree nodes connect to other low degree nodes. And you get this type of network is shown on the right. Or you can have negative assortativity, where high degree nodes tend to connect to lower degree nodes. This type of configuration creates the hub and spokes, or the star-like networks that we see here on the left. So again, in the network on the left will have more nodes experience friendship paradox than the network on the right. So degree assortativity also contributes to the friendship paradox effect. But to describe, when we describe strong friendship paradox, as opposed to Feld's version of the friendship paradox, you also need the next higher order property of the network. This is what we call transsortativity. Again, this is a jargon that we coined, but we decided to create this new word to highlight the importance of this structural property of the network. So transsortativity gives degree distributions of neighbors of a node. So you need connected triplets of nodes, whether it's a connected triangle or a wedge, and transsortativity describes correlations among degrees of the neighbors of a node. As an illustration, look at the little snippets I have on little snippets of the network I'm showing you. One on the bottom right illustrates a positive transsortativity case, where the neighbors of a node, the vertex, neighbors of a vertex have similar degrees. So that's positive transsortativity. But you can also have negative transsortativity, or which is similar to this assortative case, where neighbors have very highly dissimilar, highly different degrees. And transsortativity is the last property of the network you need to describe majority illusion and strong friendship paradox. You don't need any higher order properties still. Importantly, transsortativity can strongly affect the structure of the network, observed structure of the network. For example, coming back to our friend, the Karate Club network, so I'm showing it in the center is the original network. We can rewire this graph to increase transsortativity or to decrease it, while keeping all other structural properties the same. So all three networks shown here have the same degree distribution and have the same joint degree distribution or assortativity. But the network on the right has been rewired to increase transsortativity. If you actually look closely at every neighbor, every node within the network on the right, it's highly likely to have neighbors that have similar degrees. But the network on the left was rewired to decrease transsortativity, to create negative transsortativity. If you pick any node at random there and look at the degree of the nodes, of its neighbors, they'll be very dissimilar, more likely to be dissimilar. So which do you think the networks in the real world, what do the networks look like? And by the way, you can see that actually the structure varies quite a bit. As you increase transsortativity or decrease it, it produces very different structures. So where do real world networks fall? More in the positive transortative case or negative. In fact, actually, most of the networks are fall in the positive transortativity case. Here, we are breaking down networks and showing correlations between degrees of neighbors for nodes of degree k. As we vary k and 6, this is reports results for 5 real-world networks, but we looked at other networks as well, and they have the similar story. So most of the networks in the real world have positive transortativity. The only negative network we saw out of the dozen or so we examined has been the Facebook social circles graph from Snap. And actually, Karate Club also has a slightly negative transortativity in its original configuration, but all other networks have positive transortativity, in fact, strongly positive, going up to 0.6 in the case of the Actom graph. So there's something about social connections, forming social connections, that induces, from which positive transortativity emerges. Transortativity is what is this final component of network structure that you need to explain the strong friendship paradox. So here I'm showing you this on illustrating this concept in one real-world network. This happens to be the Skitter internet, but it applies to other networks as well. The blue dots showing for within this network, if you pick a node of degree k, what is the probability that it will observe that most of its friends? So what is the probability that it is in the paradox regime? By this I mean, what is the probability that how many nodes, what fraction of nodes have neighbors, most of whom have high degree than does itself? Okay, is it clear? For degree k node, what is the probability that it will observe that most of its friends have a higher degree than it does? So the blue dots show the empirically measured probability, or the fraction of nodes that experience the strong friendship paradox. The red dashed lines shows the estimates of the assortativity model. So the model takes into account the degree distribution of the network and the joint degree distribution, or assortativity of the network. It estimates the number of nodes that experience strong friendship paradox given by the red dashed lines. And you can see that this assortativity model overestimates the strong friendship paradox for low degree nodes and underestimates it for high degree nodes. But when we add transortativity in the model, then we get a far more accurate description of the world. So this is the solid red line, shows the estimated fraction of nodes experiencing strong friendship paradox given by the transortativity model. And you can see that it accurately estimates the empirical observations. And in fact, you don't need anything more. Transortativity, assortativity, and degree distribution are the three things you need to create this plot, to actually reproduce it, and nothing else. And this applies, we generalize this to the model. The same model explains many different networks. All you need to know is these three components: degree distribution, assortativity, and transortativity. And you can estimate which nodes, how many nodes experience the strong friendship paradox. So as I said before, once you have strong friendship paradox, you can explain the majority illusion. All you need is just correlation between having an attribute and being popular. In that case, if you have that correlation, if high degree nodes happen to have that trait, then even when the trait is rare overall, many nodes will think that majority of their friends will have that trait and will perceive it in a biased way. This definitely network structure can amplify the majority illusion effect. So first, like I said, as I said before, this correlation is important. The higher degree nodes, the more popular nodes are likely to have this trait, the stronger the majority illusion effect will be. So I'm illustrating these trends with a synthetic graph we constructed using configuration models. So it has skewed degree distribution, synthetic graph with 10,000 nodes, and 5% of these nodes have some traits. Suppose it's being blue. So 5% of the nodes are blue, and then we ask the remaining 95% of the nodes, is the majority of your friends blue or not? And the plot, the y-axis, reports what fraction of nodes report that majority of the friends are indeed blue. The x-axis shows the correlation between having degree K or being high degree and having the trait being blue, for example. As you increase that correlation, when the higher degree nodes are more likely to be blue, it dramatically increases the majority illusion effect. So the lines go up. Another factor that really that matters, that affects majority illusion effect, is the associativity. When the networks are more disassociative, like each of these lines actually just represents the same network that's been rewired to achieve a different associativity value. So as you go up, those networks are more and more disassociative. So the blue values report the most disassociative network we have created with this configuration model. So as the networks that are more disassociative, dramatically amplifies the majority illusion effect. In fact, even though only 5% of the nodes are blue, in some configurations, especially in the most disassociative networks, you can actually get up to 80 or even more than 80% of the nodes report that most of the friends, majority of the friends are blue. So again, we see that skewed degree distribution, when you have these high degree nodes, when these high degree nodes tend to have the trait of interest, and when they tend to be, high degree nodes tend to be connected to lower degree nodes, which is dissociativity. All these three effects amplify the majority illusion effect. In addition, transortativity also amplifies the majority illusion effect. So here's simulation in another synthetic network that we keep the synthetic network, we keep the structure the same, we just rewire the network to increase or decrease the transortativity. So each of these lines is, again, for the same network, but with a different value of transortativity, the different rewired network. So as you move up, as you increase the transortativity, it actually increases the majority illusion effect. So even when in this particular synthetic network, we started with half of 1% of nodes being blue, for example, and reporting how many other nodes observed the majority of the friends being blue, again, you can go from 0.5% of in reality to many nodes thinking that 25% nodes thinking that majority of the friends are blue. So it can strongly amplify the majority illusion effect. Okay, so I've shown you that this network structure, this network effects can systematically bias the perceptions, how popular nodes perceive some trait to be among their friends within their social circles. Basically, these effects can skew perceptions dramatically. They can make even a rare attribute appear far more common among the friends than it actually is in the network as a whole. Which I'm sure might explain many phenomena that we observe in social media, especially where some things, for example, not wearing a mask, maybe in reality is actually a rare, very few people don't wear masks, but since they happen to be more vocal, more active, it might bias perceptions. Many people will perceive that, oh, many of my friends don't wear masks. So this is something that can happen on a regular basis. And of course, this research also raises many questions about what impact perception bias has on behavior within networks. How does it affect contagious outbreaks, the spreading phenomena, benign phenomena? How does it affect the performance of inference algorithms in networks? We haven't done very much in network control and intervention policies, but imagine, again, you can target your interventions in a directed way so that you can just have to intervene with a small fraction of nodes and leverage perception bias and majority illusion effects to affect a much larger fraction of nodes. And I'm also curious, and some of my research is now looking at psychological, more sociological effects of the perception bias. How does this, so the prior work has shown that there's fracture paradoxes for happiness, for example. But how does it apply to polarization? Does network bias amplify polarization in social systems or not? So finally, there's many questions to be answered, but we're moving there. I'd like to thank my collaborators who've been indispensable in making this work, and I welcome your questions. Thank you very much.